So have you ever caught yourself wondering what the internal engineering systems actually look like over at the world's leading AI lab? There's this massive assumption floating around the tech industry right now. Everyone kind of assumes that to get unbelievable results from AI agents, you absolutely need these wildly complicated, multi-layered pipelines. But what if the exact opposite is true? What if the real secret to building a highly effective AI agent isn't about piling on more complexity, but actually ruthlessly stripping it away?
Welcome to The Explainer. Today, we're taking a really fascinating look under the hood. We're going to see exactly how OpenAI built its own internal data agent. This tooling serves thousands of OpenAI employees every single day, and honestly, its architecture is surprisingly brilliantly simple.
Here's our quick roadmap for today. We'll start with the AI complexity myth, dive into the data agent itself, look at context assembly, see how they scale with Codex, and wrap up with 5 actionable engineering lessons. All right, Section 1, the complexity myth. Let's look at how the broader industry trend stacks up against OpenAI's reality. Okay, let's really dive into this. If you look around, the current industry trend is to build these increasingly complicated multi-agent pipelines, right? Developers are out there using complex routers to separate the easy questions from the hard ones. They're juggling multiple fine-tuned models and building totally separate retrieval pipelines for every single type of content. And the thing is, every single one of those pieces adds latency, it drives up costs, and it just creates new, fragile ways for the whole system to break. OpenAI? They go in the completely opposite direction. The reality is literally just one single model, GPT 5.5, used for every single request. It's capped at just 13 tools, and it runs in a beautifully simple runtime loop. That's it. Moving to Section 2, inside the data agent. Let's break down its actual anatomy and see how this workflow plays out in real time. The day-to-day workflow here is just incredibly frictionless. Let's say an engineer wants to know the number of active users over the past few weeks. Instead of jumping through hoops, they simply type that plain English question directly into Slack. The agent takes a second, reasons about the request, autonomously writes the correct SQL, runs it, and then literally seconds later replies with the exact answer, the SQL code it executed, and the source tables it pulled from. It is a completely seamless loop. Now, if we look a little closer at the harness under the hood, this architecture is powered strictly by GPT 5.5. And like I mentioned, it's firmly capped at 13 specific tools. It runs in a continuous loop, which is totally key because it means the model can act on its own reasoning. It checks its own results and refines the SQL until it knows the answer is rock solid. But the real engineering magic here, the absolute core of why this works so incredibly well, lives in what they call the context assembly layer. Which brings us to Section 3, the context assembly layer. To truly grasp why this layer is so brilliant, we first have to wrap our heads around the massive problem it actually solves. Get this. OpenAI's internal data warehouse contains over 70,000 tables. Think about that scale for a second. 70,000. So when a user asks a simple, plain English question, the immediate challenge for the agent isn't even writing the SQL. The real challenge is simply finding the right data among 70,000 options to even query in the first place. And this brilliantly illustrates exactly why you can't just feed the model a standard database schema. If you rely on schema alone, the agent is basically flying blind. Imagine you have 2 nearly identical tables, and they both have a user ID column. A basic schema isn't going to tell the model that one table includes logged out users, while the other strictly tracks logged in users. Without enriched context giving the true intent of the table, the agent is just left guessing. And guessing, that leads straight to hallucinations and incorrect data. So to solve this, OpenAI's team built a context assembler that merges 3 incredibly smart data sources into one perfect, highly detailed description for every single table, updating daily. First up, they pull usage metadata. This tracks how human engineers have actually queried the table in the past. Second, they pull human annotations, which are mandatory notes written directly by the people who own the tables. And third, they use Codex enrichment. This is a nightly automated job that literally goes in, reads the underlying code behind each table, and records exactly what it contains and precisely when it should be used. But it gets better, because they don't stop there. Once a question actually arrives, the context assembly step retrieves those highly detailed table descriptions and enriches them even further. They pull in relevant company knowledge straight from internal places like Slack, Docs, and Notion. And finally, they fold in the agent's memory. Specifically, it remembers corrections from past conversations. All of this ensures that a flawless, perfectly informed context is assembled before a single line of SQL is ever written. Moving on to Section 4, scaling with Codex. The context layer is amazing, but to see this tooling truly scale, we need to look at how they handle autonomous operations across their platform. For instance, there was a situation recently where OpenAI's platform actually ran out of capacity on one of their cloud providers. Now, normally, a company would throw hundreds of human engineers at a problem like that, right? Instead, Codex autonomously generated the pull request required to migrate 90,000 separate data tables. That single automated migration moved 600 petabytes of data. Seriously, let that sink in for a moment. 600 petabytes. And because they heavily trusted their autonomous tooling, this massive, complex infrastructure shift was completed flawlessly in just about 2 months. Beyond just migrations, Codex acts as this tireless digital workforce. It functions as a patch releaser, where it tests and ships patches across more than a dozen open source forks. It'll run unattended for months at a time without a single incident.
It also serves as an autonomous support bot. When an on-call engineer gets a ticket, they just hand it off to Codex. Codex investigates the issue, figures it out, and applies the fix for human review. It is successfully handling roughly 100 fixes per day per engineer. It's just wild. All right, Section 5, Key Engineering Lessons. So what can we actually learn from the engine room? Here are 5 takeaways you can apply to your own applications. Lesson number 1. The foundation matters way more than the agent itself. OpenAI maintains an incredibly clean monorepo with strictly enforced conventions and required annotations for every single table. That boring foundational stuff, that is what makes a vanilla agent reliable. If your company's data is scattered all over the place, messy, and undocumented, buying or building some fancy AI agent is not going to save you. You've got to fix your foundation first. Lesson number 2 proves that fewer tools actually beat more tools. This is a big one. When OpenAI started, they gave their agent around 40 tools. And the result? The agent just got confused. It constantly picked the wrong ones, and it got conflicting answers from tools that had overlapping jobs. By aggressively cutting that down and capping the agent at just 13 distinct, totally non-overlapping tools, the reliability absolutely skyrocketed. Lesson 3 is basically a masterclass in AI memory. You shouldn't let your agent learn from every single past query. Initially, OpenAI tried embedding every SQL query ever written as an example for the agent, and it failed miserably. Why? Because most queries are just messy one-off experiments. The fix was ranking the queries by trust. They put queries that power heavily used production dashboards at the very top and random one-offs at the bottom. Now the agent relies exclusively on high-quality examples. Lesson 4 is a great reminder on how you should talk to the model. Guide the goal, not the path. It turns out that giving the agent these highly detailed step-by-step micro-prompts actually made its answers worse. Instead, developers should give the agent high-level goals, supply that rich context we talked about earlier, hand it the right tools, and then just get out of its way. Finally, lesson number 5. Be more ambitious. When OpenAI needed to move those 600 petabytes of data, traditional estimates said it would take way longer than 2 months. But they pushed for 2 months, they leaned on AI, and they hit the target. The reality here is that timeline estimates from before AI simply do not apply anymore. The biggest risk in software engineering right now isn't aiming too high. Honestly, it's simply playing it too safe. Which leaves us with a really critical question for your own work. As you take these architectural lessons back to your development cycles, as you simplify your agents, invest heavily in context assembly, and ruthlessly cut down tool overlap, look at your current project roadmap. Ask yourself, are you playing it too safe with your engineering timelines? Thanks so much for joining me for this explainer, and I'll see you next time.